length of the magnetic core. And we're going to see this, inshallah, today with examples, because today we're going to do more examples related to this. So whatever you have average length for the magnetic core, this will be the LC, the length of the magnetic core. So for example,
Yes.
معليش بس ثواني. طيب معلش بس لاني غيرت من المايكروسوفت باوربوينت ل PDF. طيب, for example, this circuit, it's a magnetic circuit.
Yes.
And the average length, for example, in this will be whatever length you have across the magnetic core. So where is the magnetic core? This is the magnetic core. So we take the average length of this.
The average. تمام.
And we're gonna discuss how we find the average length of such magnetic core, because if you can notice, you have like two lengths, the outer length and the inner length.
Yes.
So the average length will be between them, right? So we're gonna discuss this today. The mu r is the property of the material, which reflects the capability of the material to conduct magnetic flux. So mu r, for example, it's for this material. So if we say that mu r for this material is 100, the meaning of this is that this material will be able to conduct magnetic flux 100 times more than the air, because mu will be mu naught, which is for the air, multiplied by mu r, which is for the material. So it is given for each material. You know, for the material, what is the mu r, and after that you can calculate what is mu and the reluctance for the whole material later.
Yes.
Clear?
Clear.
Any other questions? So, okay, we're gonna go through the formulas that we discussed last time. So this is what we discussed last time. We discussed, for example, that flux is equal to B multiplied by A, where B is the density, magnetic flux density. A is the cross-sectional area. Flux is also F divided by R, where F is the MMF and R is the reluctance. H, which is the intensity, is F divided by LC, where LC is the average length. B is equal to mu H, where mu is the permeability of the material and H is the intensity, of course. R is LC divided by mu A, where mu is mu naught multiplied by mu R. So remember that you need to memorize all of them and understand the relation between all of these variables, because now we are learning about a new circuit, a new type of circuit, which is a magnetic circuit. We know how to analyze mechanical systems. We know how to analyze electrical systems. This is a new type of circuits so that you need to know the relation between different parameters you have in this circuit. So now we're going to discuss today how we can analyze such magnetic circuit. Luckily, magnetic circuits, they behave like electric circuits, or let's say there is analogy or relation between them, meaning that we can represent the magnetic circuit and deal with it similar to what we represent and analyze electric circuits, which is good. And if you remember, we discussed this last time by relating the which is the MMF to the voltage, flux to the current, reluctance to the resistance. So we said that MMF in the magnetic circuit is similar to the voltage in electric circuit. Flux is similar to the current in electric circuit. Reluctance is similar to the resistance in electric circuit. And this is very important. Why? Because if we can represent the magnetic circuit as electric circuit, and since these three parameters, they are analogous to each other, so what we can do, we can actually represent the circuit and analyze it similar to what we analyze electric circuits. So the one to the left is typical electric circuit. This is what we know. This is what we discussed before. We have voltage source, we have resistance, and we have current, and we can apply Ohm's law, not only Ohm's law, voltage divider, current divider, KCL, KVL. We know this. Now, if we can represent the magnetic circuit as similar to electric circuit, meaning that the source will be F, MMF, resistance will be reluctance, current will be flux. And of course, we can use the Ohm's law relation to relate between them. And not only the Ohm's law, any other technique that we learned about electric circuit, we can actually do it, apply it to magnetic circuit. The difficulty here, and this is the most difficult part, is basically how we can represent the magnetic circuit as electric circuit. And we're gonna learn how to do this today. How we can calculate, for example, the reluctance for the whole magnetic circuit. How we can calculate the MMF, etc. But if we can do this, which is the most difficult part, this is half of the solution. That's it. Once you draw the circuit, you can use any technique that we learned before an electric circuit and apply it to the magnetic circuit parameters. So for example, we can use KVL, as you can see here. We can use KCL, voltage divider, current divider, all the techniques that we know for electric circuit and magnetic circuit. The only difference will be the parameters will be different. We're not going to deal in magnetic circuit with current. We will deal with flux. We're not going to deal with voltage. We'll deal with F, MMF. No resistance. We'll deal with reluctance. That's it. Once you do this, you should be able to solve any magnetic circuit. This is an example here of converting magnetic circuit with air gap. What do I mean by air gap? Which is basically this. And also this air gap. Meaning that we have magnetic core and air gap. One of the major differences between the magnetic circuit and electric circuit, in electric circuit, if we have an air gap, what will be the current? Zero. It's open circuit. An electric circuit, let's assume that we have electric circuit like this. We have a resistor, then we have air gap. Well, the current here will be equal to zero, period. That's it. So no flow of current. And magnetic circuit, if we have air gap, we still have flux going here and here, of course. Of course, larger air gap means what? Larger air gap, it means larger reluctance, right?
Yeah.
Larger reluctance, it means less
Less
flux.
flux.
Yes, but still, if we have air gap, it doesn't mean that we don't have flux. This is the idea here.
Yes.
So there is a reluctance for the core, for example, here, and reluctance here for the air gap. Okay. So how we can represent, for example, this circuit, change it to be or represent it as electric circuit? First of all, here there is assumption that the permeability of the material of the core is infinity. So again, what's the meaning of the permeability is infinity? This is an assumption. What is the reluctance in this case?
Infinity.
Zero.
Zero. Because it's LC mu A, right? So if this one infinity, R will be zero. So this is assumption. So how we can represent this as electric circuit? Well, it's easy. We have a source, which is the coil here. We represent it as voltage source with the value Ni. Okay? We have air gap in parallel to the source with reluctance for air gap. So we represent this as R1 in parallel with the source. We have another air gap in parallel to the source and also in parallel to air gap 1. So it is R2 or similar to the resistance in parallel to Ni and R1. What about the directions of fluxes? Well, similar to specifying the directions of currents. We know that using right-hand rule that the direction of the flux will be here. So we specify the flux here to be going from the source to the loads. Then flux 1 will be down, flux 2 will be down. And these are the two fluxes here. So you need to do this because I will give you the questions like this, and you need to convert this circuit to the circuit and analyze it. So for example, if the question is find what is flux 1. If I ask you find what is flux 1, well, you change it to the circuit, then
Find
what?
R1.
Yeah. Find R1, find R2, find Ni, then that's it, right?
Mathematical.
Yeah, you can say
And
that
mathematical
flux
value.
1 is equal Ni divided by R1, which is like voltage divided by resistance.
Yes.
Or someone might actually say that what I'm gonna do, I will combine R1 with R2, right? Both of them, they are in parallel, so I combine them in parallel. I find the flux 1, then use current divider rule to find flux 1, flux 2, etc. I mean, you can do whatever you do usually with the electric circuit. So let's assume that we don't have this assumption. And the permeability of the core is not infinity. What do you think will be now the representation of the circuit? What will be the difference in this?
The resistance will be in series, R1 with another resistance from the core.
There will be some resistance after the source.
وش الكيس دكتور
Yes,
again?
like this.
الكيس.
There is no, this is not infinity. So we have also reluctance for the material here.
The reluctance will be all over the lines.
Well, good point. What we can do, the most like complicated case will be what? Will be, or let's say the most precise way to represent the core will be assuming that this is from here to here, one reluctance. Does this make sense to you? And this reluctance, this reluctance is connected in series with the source, right?
Mm-hmm.
What you can say also is that we have also this from here to here, one reluctance. And this is connected here. And also we have from here to here, one reluctance. And this is connected here. You see my point, right? And this is one reluctance, which is connected here. One reluctance connected here. And then we have one here. One here. And etc. What do you think? It's true. This is correct, by the way. It's not wrong. But usually we know from our analysis of electric circuit is that later we can combine reluctances together, right?
Yes.
We can say that this is in series with this one, in series with this one, so 3 together here. We can say that this one is combined with this one, both of them in series. We can say all the 3 here with the 2 here, they are connected in series. So instead of doing this step, from our experience, we can directly represent magnetic core to reluctances with optimal number of reluctances. Meaning what? We can say that this basically side, the left side, will be one reluctance in series with the source. This central side is one reluctance in series with R1. And the right side is one reluctance with R2. Does this make sense to you?
Yes.
Yes. Of course.
Yeah, because if you remember the previous circuit, we did almost the same, but with more number of reluctances. But at the end, we combine them together. What will be now the difference? How we can calculate, for example, this reluctance here or this reluctance here? Well, we know the equation, which is LC mu A. So yes, for the central, for example, leg, the green one, we need to find what is the average length of this leg. We need to know exactly what is the mu for this and cross-sectional area for this. So what is the average length for the central leg here? Well, it's the length from this point to this point, right? Subtracting the length of air gap. What is the average length of the left leg? Well, it's the average length from this point to this point. And we are going to learn how to do this in the next few slides. Similarly, what is the cross-sectional area? Well, we need to know what's the dimension into the page, the third dimension that we don't see, such that we can find what is the area. Do you agree? Or the cross-sectional area.
Yes.
So once we do this for all the reluctances in the circuit and substitute here for the values, that's it. We analyze this. So yes, the most difficult part will be, first of all, I will not give you this. You didn't know this. It's your responsibility to represent and find what's the equivalent electric circuit for this. So you are the one who is going to specify how many reluctances and how they are connected together. Second difficult step is to calculate all of the values here based on the dimensions, based on the cross-sectional areas, based on reluctances. But once you do these two important steps, anything else will be easy. So any question regarding this?
دكتور
Mhm.
الحين احنا نقدر نمثل الريلكتنس بالالكتريك سيركت صح؟
Yes.
ولا نعتبرها نفس الريزيستنس هنا؟ نعاملهم يعني معاملة مختلفة صح؟
We deal with them as resistances. Yes, they are reluctances. So the value of this is a reluctance. It's not a resistor, but
بس ايوه
the behavior is like resistors in the electric circuit. So we can combine them in series and parallel, similar
يعني
to what we deal with the resistors in electric circuit.
يندمج مع الريلكتنس مع الريزستورز هنا بالالكتريك سيركت.
Yes, similar to the resistors in electric circuit. Yes.
تمام.
دكتور
Mhm.
بالنسبة للميو راح تكون كلها نفس كل القيم نفس لهم نفس القيمة بالنسبة للدائرة.
Yes, if mu r, if it is the same material, mu r is the same, right? For the
Yes.
whole material. For the air gap, we don't have mu r. Mu r is equal to 1.
Oh, okay.
Mhm. Yes. R1 represents the air gap, 1. Reluctance, yeah. In this circuit, we don't have resistors. All of them reluctances. No. R1 assuming that this is infinity, so we have only one reluctance, which is for the air gap. We don't have reluctances for the core, so we have 2. One for air gap 1, one for air gap 2. But
Yes.
after that, just to explain more, I assume that this is not infinity, so we added more to this.
Okay, yes.
Sure.
Mhm.
We have more material. Should we added more reluctance, isn't?
Yes, that's correct. If let's assume, just we make an assumption that this, for example, side, let's assume that this half is one material. Okay, and this half is another material. Yes, you cannot assume that this is one complete reluctance. You need to separate them. So now it will be like one up and one down. Why? Because this R will be LC mu A, and this R is also LC mu A. Mu here is not the same as mu here, right? So you cannot combine both of them into one reluctance. You do it later. So once you find the value here and the value here, you can after that combine them, but not from the beginning where you find the total value. Okay.
Doctor,
Mhm.
but in practical, we use materials which have permeability factor is like 6,000 or 5,000. So the reluctance will be almost 0. So in practical, we assume it like no reluctance. Most cases, in most cases.
And when you design any magnetic circuit, when you design any electric circuit, of course, your objective is to make reluctance or resistance as low as possible because you don't want losses, right? That's true. But as I mentioned yesterday, it has to do with many other factors, such as cost of the material, for example. If, for example, if a magnetic material that give you high permeability and low magnetic losses, and reluctance is almost zero. If it is expensive, you don't do it for certain applications. You choose material that it's cheap and will give you reasonable reluctance. So yeah, you cannot assume that the reluctance is always zero and the mu is infinity or almost or large enough to be assumed infinity like this. In theory, you need to deal with any kind of permeability. So I will, before I proceed, just I will explain when should we combine reluctances, when should we not combine reluctances and representation. So when should we say that these three legs should be represented as one reluctance, or when should we say that first we will represent this as one reluctance and
Constant cross-sectional area. And
this yes, and this one is one reluctance. Well, if they have different material, so we're talking about the denominator here. If different materials, just separate them. If different cross-sectional area, just separate them and combine them later in the representation. So let's assume that, similar to here, the cross-sectional area here is different than cross-sectional area here. It's clear, huh? So yes, you represent this as one reluctance. You say that this is R, and you represent this as another reluctance, which is another R. And here is also one reluctance. We know that at the end you will combine all of them together, but it's a mistake to assume that from the beginning that the cross-sectional area is the same, which is this. Okay? So whenever material is different, just separate them. Whenever cross-sectional area is different, just separate them. Clear? And we're gonna see, of course, with more examples, the meaning of this. There is a very important concept here in magnetic circuits, which is called the fringing effect. Fringing effect is basically the impact of air gap and the magnetic flux leaving the north to the south side. We would expect the magnetic flux lines to be directly from the north to the south, which is correct. But since this is air, and the magnetic core here is surrounded by air, and there is permeability for the air, right? Or there is a reluctance for the air. Yes, this reluctance for the core is much, much larger than the reluctance of the air. So flux coming here naturally will go where? To the core. Or let's say most of it. Because remember, it's like the electric circuit. Flux is coming and it has two options: core, air. This one, sorry, much less.
يروح مع الأقل.
Yes, this will go to the least resistive or reluctance path, right?
Yes.
Which is the current divider rule. But small amount of the flux will go also to the air, which is the surrounding air. يعني كأنه شوية يطلع من هنا. This is leakage. It's called leakage. We will come to it later. It means that the magnetic flux is leaking from the core itself to the air. When also the magnetic flux is moving through the air gap, part of the flux will go outside the cross-sectional area, meaning it's like it moves from one point to another point. but it will go to the south. That's fine. So what will be the difference here?
The cross-sectional area. If we
Good.
don't have leakage, we consider it as one area.
That's completely correct. The cross-sectional area for the air gap will be now larger because of this fringing effect. And this will affect, for example, the intensity, density, and we will come to this later. And usually the fringing effect is represented by percentage. So for example, if I say that the fringing effect is, or factor, fringing factor is 1.5. What does that mean to you here?
We multiply it by the area.
Yes, it means that this air gap is more than the core area by 5%. Or yes, you can say that the area of the air gap is 1.05 the area of core. Or I can just simply say that the fringing effect is 5%, meaning that I'm talking about 5% more in the air gap than the core. Okay? So when you calculate, for example, for the air gap reluctance, let's see, what you are going to say, LC mu A. This A for the air gap will be what?
Some percentage multiplied by the cross-sectional of the core.
Yeah, the percentage 1.05, 1.010, etc. multiply by the core.
So the question, doctor, how can we find the percentage, or who's gonna provide us the?
Oh, this
percentage?
is by measurement. I mean, this is given for specific air gap. You don't, of course, calculate this. It's given for the air gap. And this is by experiments. You experiment how much basically the intensity of the flux outside the air gap.
Cool.
Can it be neglected because it's so small?
Usually it is neglected, yes. But if it is mentioned, you need to include it in your calculation. If it is not mentioned, you don't worry about it.
So, doctor, for example, we multiply the area 1.05 times area. The area you mean is the area of the
Core.
cross-sectional?
Which one again?
The area of the cross-sectional?
Yes, the area of the core here. An example. So we're going to solve a couple of examples just to clarify all of these concepts. A ferromagnetic material is shown. So this is the basic magnetic circuit. All the sides of this core are of uniform width. So what's the meaning of uniform width? It means that this is the cross-sectional area.
It's the same.
It's the same.
So we don't have to worry about which one is different than the other one. All of them, they are uniform width. The cross-sectional area is 16. So he's given you actually what's the cross-sectional area, 16 centimeters square. And the average length is 40. Again, it's given. So you don't have to worry about how we can calculate, for example, this cross-sectional area. No. Or how we can calculate the average length. Both of them, they are given. Okay? There is a 350 tin coil wrapped around the left side of the core. So N is equal how much?
350.
350
Assume relative permeability of the core 50,000. So mu R is equal 50,000. For a magnetic flux density 1.5, what is the magnetic flux density? B.
B.
Find what is the flux.
Flux. F of R.
B
First we
times area.
represent it
Density multiplied by the area.
Yes, which is an equation that we learned before, right? We know that the flux is equal BA. B is given as A is already also given as 16. Why I am multiplying by 10 to the power minus 4?
قلت تحول
سنتيمتر
تحول على متر سكوير.
Yes, you need
convert the
always,
unit.
because the standard unit is meter or meter square. So you need always to change the length or the area from centimeter square to meter square, or from centimeter to meter. So that's why we multiply by minus 4. Clear?
Yep.
clear.
So it's 2.4. B, the required current throughout the coil. How we can find this?
This is
The
an I over
flux times R over N.
Yes, which is basically, do we
The
have a
flux.
relation between them?
Yes, the
yes,
flux,
the flux
equal
to
I is equal the flux multiplied by R over
over N.
N.
an I over R.
So what do we know? We know that F is equal flux multiplied by R, right? So this will be flux where the F, F is equal NI, right? So we know this from A. We know N is given. Do we know R?
نقدر نحسبها.
No, but
We
we
can
can
find
find it by L.
We
also.
don't.
That's correct. We need to calculate what is R, which is LC.
over mu N.
So what is LC? Again, it's given as 0.4. Why 0.4? Because it's in meter. How we can calculate mu? Mu will be 4 pi 10 to the power minus 7, which is mu 0, multiplied by 50,000. Multiplied by A, which is 16 10 to the power minus 4. Clear?
ليه؟
Clear.
Clear يا دكتور.
So once we find R, we just substitute here. And the only unknown will be what? The current. Is it clear?
Yes.
Yes.
Yes, clear.
Yes.
Yep.
So another example similar to the previous one. A ferromagnetic core is shown. All the sides of this core are uniform with 150 centimeter square, 180 the length, 200 turns, relative mu r 2500. How much flux will be produced by a 1 amp input current? So it's almost the opposite compared to the previous part B. So we have the input current, we have N. So we can find F, right?
Yeah, but we need to find R. Right.
We have, so
We have to find R only.
sorry, N is here. So this is 200 multiplied by 1. So F is equal to 100. We need to find the flux. We know that the flux is equal, again,
F over R.
so we need to find R again. R will be equal to
LC.
length, which is 1.8, 4 pi multiplied by 10 to the power minus 7, 2500, 150, 10 to the power minus 4. And that's it. Any question?
Clear.
So I'm gonna start this. We might not have enough time to solve the whole example, but just to also get an idea. It's a little bit more complicated. Why? Because now you need to calculate what is the length and the cross-sectional area. And to do this, you need all the dimensions you have in the magnetic core. So ferromagnetic core is shown. The three sides of this core are of uniform width, while the fourth side is somewhat thinner. So this side and this side and this side, they all have the same uniform width, but this side is, and you can see it clearly, it's with different cross-sectional area. The depth of the core is 10 centimeters. So what is the depth of the core? This is the dimension that you don't see, right? This is into the page. So the third dimension is basically 10 centimeters. Clear?
Yes.
Yeah.
And you need it, of course, to find the area after that. And the other dimensions are shown in the figure. So you see all the dimensions here for different parts of this magnetic core. 210 coil wrapped around the left side of the core. Mu R is 2500. How much flux will be produced by 1 amp input current? So similar to the previous example, but now we need to find what is LC and A. First of all, how many reluctances we have here?
2.
2.
2. One will represent this. The other one will represent this. If someone actually represented this by 4 reluctances, is it correct or wrong?
Yes, correct.
It is correct. If someone actually wants to represent this as one that's correct, yes. The optimum number is 2. You can go up to 4. 1, 2, 3, 4. It's up to you. If it is easier to go with 4, and after that you combine them, it's the same as going for 2, and after that combining them also. Okay. So let's start with 4, and after that I briefly discuss also the 2. Let's assume that we have one reluctance first of all here. How we can calculate the reluctance for this one? Well, we need to find the length. What is the average length of this? We're talking just about the upper leg.
45.
Why 45?
45 centimeter.
I took the
No.
center of the 2 squares.
2.5.
Yeah, there is a very easy system.
2.5.
Yeah, there is a very easy way. We find what is the outer length. We find what is the inner length. We add them together, divided by 2.
42.5.
Yes.
55 على 30. Okay.
This one will be basically 10 plus 30 plus 10 plus 30 plus 15.
42.5.
55.
42.5.
42.5.
Plus 30, yes, divided by 2.
42.5.
Which is 42, as you mentioned, 0.5. Multiply by, don't forget the 10 to the power minus 2. So is it clear how we found basically this?
Yes.
Yes.
Then mu, you calculate mu as before. A, how we can calculate A?
Mu naught multiplied by mu r.
Yeah, I'm not talking about this. A, how we can calculate
15, which is 1.5.
Ah.
10 multiplied by 10.
A? That's correct.
The width by the
15, which is the width here. 15 multiplied by 10, which we don't see, right?
Yes.
But we know it's rectangle, so 15 multiplied by 10 multiplied by 10 to the power minus 4. So this is for the upper reluctance here. What about this?
Should be
The same. Almost the same. I mean the same procedure. For example, the average length will be this outer length, which is 60, plus 30 divided by 2,
45. Yes.
The area will be 15 multiplied by 10, same area.
Yes.
Similarly here, just let me finish and after that I'll take question.
55.
What about this leg? How we can calculate the reluctance for this? Well,
نفس procedure.
Same procedure. 60 divided by 60 plus
زائد.
divided by 2. This is the length. What about the area? Area is 10 multiplied by 10.
By 10. Yes.
So this is, as I mentioned, this is representing the circuit with four reluctances. So the circuit, if you want to draw it, will be like this. Reluctance, source, reluctance, reluctance, reluctance. Okay? But we know from our experience so far is that we don't need to represent 4, we need just to represent 2, which is R1 reflecting the 3, and R2, which is reflecting this part only. So how we can calculate this, R1? R1 will be LC. How we can calculate LC for the 3 together?
Just summation.
Yeah, basically similar to what we did before. So we can say that it's 55 plus 30 divided by 2 plus 60 plus 30 divided by 2 plus 55 plus 30 divided by 2, right? So it's like we are find the average length of this plus this divided by mu divided by 15 by 10 by 10 to the power minus 4. And this is multiplied by, okay?
Yes.
R2 will be similar to before.
Yep.
And that's it.
Doctor?
Once we find R1, once we find R2, how we can find the flux? Easy, Ohm's law, right? This source divided by
R يعطيني flux.
both of them, R1 plus R2, right?
Yes. In series.
Yes, questions?
Yes, doctor. At R2, you took only 60. You did not add to it the inner side.
Yeah, 60. Yeah, that's good. This one 60 plus, sorry.
Okay.
30.
Thank you.
So what I need you to do, guys, do it at home.
Isn't the area 15 plus 10 multiplied by 10 to the power minus 4?
Yeah, this is the area for the 3 legs here.
Because you wrote 15 multiplied by 10 multiplied by 10 to the power minus 4.
Yeah, that's correct. Because the area here is 15 multiplied by the depth, which is 10.
Yes,
but since both of no, only one area, because this is representing the same area here. Okay? Because remember, this one was like the previous this, right? This one was also the previous this. And this one was the previous. So this is how we add basically fractions together. So what I need you to do, guys, is basically just solve this example. So 1, 2, 3, Just do it at home. We did it here. Just make sure that you do it with calculations and get the final answer. If you do this, so we are on track. I mean, we are okay.
Yes.
Any question before we leave?
يعطيك العافية دكتور.
يعطيك العافية.
Okay, so I will see you inshallah on Sunday.
إن شاء الله.